Let's solve question 7.52 from the Incropera textbook. It is another fire-related question that deals with connecting lines interacting with each other and causing a potential fire hazard. Now, before starting to solve the question, please stop the recording and read the question statement carefully. Now that we have read the statement of the question, it is time to understand which datums we're given and what we're actually trying to find. Well, we're given the diameter of the transmission line as well as the electrical resistance. Please bear in mind it is completely different from the thermal resistances we're used to deal with in heat transfer. It's going to be essential for later on. We're also given the current that the transmission line carries. Now, in part A, we want to understand what the conductor temperature, so essentially the temperature of the cable, is at a certain given air temperature and air velocity. Now, the fact that we are given an air temperature and air velocity should already indicate us what kind of flow we're looking at. Let's now start solving the question. First of all, we have to redraw the scenario, as I already did before starting the recording. As you can see, I drew the conductor with all the data we're given. Following that, we should list all the assumptions that we're going to employ to solve the problem. The first one is steady state. We're looking at a steady state scenario. The second one is crucial, so please pay attention to this. Basically, we are saying that although it is not explicitly stated in the question, we are dealing with uniform surface temperatures. Why is this so important? Because as I think all of you have now understood, we are looking at an external flow question. This was suggested by the given air velocity and air temperature. But you can understand that also by looking at the drawing of the question. The third assumption is negligible radiation. And finally, isotropic materials, so constant properties. Please bear in mind that by assuming uniform surface temperature along the whole wire, we are saying that what happens in one section of the wire happens along the whole wire. And therefore, what we're studying right now, the scenario we're looking at, is valid for the whole length of the wire. Having said that, we can go on to solving part A. Let's now assess the conductor temperature. Since we're giving a lot of information and a lot of data, it's always good to start with an energy balance, because this helps us simplify the problem and understanding which energies we're dealing with. Now, energy balance occur around a certain control volume, and I've drawn this to include the conductor only. So this is going to allow me to write that energy generated within the conductor plus energy going in minus energy going out is going to be equal to energy stored. By making use of the assumptions we just listed above, we know that energy stored is equal to 0 because we're looking at a steady state. And now please pay attention to this. Since I've drawn the CV just around the conductor, the current carried by the conductor is actually going to contribute to this term here. So the energy going in is going to be 0. We can therefore rewrite that Q dot, which is going to be the generation term of the current, times the cross-sectional area is equal to energy out, which is equal to Q dashed due to convection. Now, please pay attention. We're going to look at watts over meters, since we don't know the length of the conductor and it's not given to us, so we can work per meter length. It is worth opening a parenthesis on this generation term I talked about. Indeed, this is our thermal power, and the current going into the wire is its origin. So it's really essential that you understand what's going on around our control volume. We have this thermal power, so this internal generation, and how is this thermal power dissipated? I mean, it has to go somewhere, right? And that's exactly what's happening. It goes through the wire, so through conduction it's dissipated towards the air, which of course due to convection dissipates the power even further. Now, as we will see in part B, this is slightly going to change due to the addition of an insulation layer. Let's find the generation term and the convection term so that we can finish part A of the question. Now, the generation term, we said it's related to the current carried by the cable. We know that resistive cables dissipate powers that are proportional to the current squared times the electroresistance. We're going to divide this by the cross-sectional area because we know that usually generation terms are assessed with watts over meters cubed. The only data missing here is the cross-sectional area, which it can be easily found because it's just pi d squared over 4. We know we know the radius, so we know the diameter, and therefore we can find the generation term. By subbing in the correct numbers, you should get that the generation term is equal to 4.111 times 10 at the 5 watts over meters cubed. Let's now find the convection term. Well, this is not obvious as it seems. Let me draw the thermal circuit we're looking at. We have the conductor temperature inside, then we have a resistance, which is due to convection, and we have the air temperature. The heat flux is going this way. Now we can write this, and we can write a formula from this because we know that QC is equal to Tc minus T infinite over RT. You can now see that we should find a way to isolate Tc in this equation and then find it simply. However, we need to do an intermediary step because we still don't have this resistance. So how do we find the resistance? Well, first of all, we need to remember what the definition of a resistance in a convection scenario is. Well, in this case, look at this. You should pay attention to this. I'm just putting 1/y because we're looking at a resistance per unit length, not per unit area. So that's why there's no double dash. So RT is equal to 1 over H average D times pi D. Okay, so now you can start understanding why at the beginning of the recording I said this is an external flow problem. Here we have an HD that's it's our unknown, and we have to find it. The following steps are not going to be any different from the ones we usually do in an external flow problem. Indeed, now we're going to find the Reynolds number and the Prandtl number of the flow, and then use a correct relationship to find the average heat transfer coefficient. However, there is a big difference. We're used to deal with flat plates, but in this case we're looking at a cylinder. This of course is going to be important for the relationship we're going to use in the Incropera textbook, from the Incropera textbook. Now, the Reynolds number and the Prandtl number of the flow can be found only if the air properties at a certain film temperature are evaluated first. As we don't know the conductor temperature, the film temperature in this case is just a complete guess. So I suggest use a film temperature of around 350 Kelvin. After evaluating the properties at that film temperature, we can evaluate the Reynolds number, which is velocity times diameter over kinematic viscosity. Sorry for that, let me write it properly. And you should get that the Reynolds number is 1.214 times 10 at the 4th. Now, the result you should get is around that. Of course, if you don't get such a result, you see that it's too far off from your expectations, please just adjust it with the iterative methods. How do we choose the correct relationship we should employ for this problem? Well, we have 3 really important information that can guide us through that choice. The first one is that we have a laminar flow. The second one is that we assume uniform surface temperatures, and finally, we know the shape of the system, which is cylindrical. Having said that, you should find in your books the Churchill-Bernstein equation, which more specifically is on page 451 of your textbook, equation 7.54. Now, having this equation really helps us because once we know the Reynolds number here and the Prandtl number, we can just sub in the values, and you should find that the average Nusselt number in our case is 59.6. Now this is equal to, as we know, H times D over K, where K is the conductivity, which of course we evaluated at the film temperature indicated here. Now we can just rearrange and find that H average is equal to, which we're going to call HD, just to be coherent with what I wrote previously, is 79 0.6 watts over meter squared Kelvin. Well, having said that, most of our problems are now solved because we know HD, so we can just sub it in this equation to understand what the thermal resistance is, and we find that R/T is equal to 0.1998 meter Kelvin over watts. Okay, so what happens now? Well, we can sub in all the values we have, starting with the generation term and everything else, and we can just arrange for TC, because again, we start from the energy balance, and we know that the generation term times the cross-sectional area is equal to the convection term, which we define just here. And this is really important, please remember this. Now, by rearranging, we find that TC is equal to Q times AC times RT plus T infinite. We have all the datums here, and so you should find that TC is equal to 45.8 degrees. Now, this is the answer to part A. Let's now solve part B of question 7.52. We have a different scenario now because we decide to insulate the conductor, and therefore we have an insulation layer which is 2 millimeters thick with a conductivity of 0.15 watts over meter Kelvin. Let's see how the conductor temperature changes. However, it is worth stopping the recording now and making some predictions. What do you think is going to be the effect of the air cooling? Is it going to be the same as in the previous part or not? Let's understand what the main difference between part B and part A of question 7.52 is. With this new scenario, so with the insulation layer, the thermal circuit of the system changes. Indeed, we're going to have T of the conductor plus a resistance due to convection exerted by the insulation layer. Then we're going to have the same convection resistance, and finally we're going to reach the air temperature. Of course, the heat flux is going to go this way. As you can imagine now, the expression for the heat flux remains the same, because it's going to be Tc minus T infinite over RT. However, what changes is the expression for the resistance. Indeed, RT is not going to be anymore 1 over HD times pi d. However, it's going to be 1 over HD nu, because we have to take into consideration the new thickness, times pi d nu, plus, so not only that, we also have to take in consideration the conduction resistance exerted by the layer, which for a cylindrical shaped system we know is ln of d nu over d over 2 pi k. Now, please bear in mind that this k is the exact same one as in the previous part, in part A, because the air properties do not change. We are still evaluating them at a film temperature of 350 Kelvin. What is good to bear in mind is that d nu is equal to d plus the thickness times 2, which is equal to 24 millimeters. Now, the steps from here are really easy because it's really literally following what we did in part A. The only difference is literally this part and this new d nu. Well, this part is easy to calculate because we know it's just ln of 24 over 20 over 2 pi k. So you should be able to do that. Now, let's find HD nu, because for HD nu there are some small yet important changes. Indeed, as you can imagine, the Reynolds number changes because the velocity of the air is the same. However, the diameter is the new one over the kinematic viscosity, which does not change when compared to the one of part A. So the new Reynolds number is 1.468 times 10 at the fourth. The flow is still laminar, luckily for us, so we can still use and employ the Churchill-Bernstein equation. Now we just plug in the numbers exactly as before, and we find that NU, the Nusselt number of the new system with the new diameter, is equal to 66.3. Therefore, the new heat transfer coefficient is equal to 73.6 watts over meter squared Kelvin. Now, from this, we're able to understand that the resistance, the thermal resistance of the circuit, is equal to 0.3736 meter Kelvin over watts, and therefore, by just rearranging the energy balance we wrote out in part A, as we did before, we can find that the conductor temperature is equal to 68.3 degrees. Now, you can see that the conductor temperature has increased with the insulation. Therefore, we can say that the polymer insulation layer is added to improve the electrical insulation of the system and therefore also its safety. Indeed, if cables touch after the insulation layer has been added, there won't be any electrical interaction, or it's not going to be as strong as before. However, this comes at the cost of increasing the thermal increasing the thermal insulation, and therefore it has bad consequences on the temperature of the cable. So as engineers, you must remember that electrical insulation is not the same as thermal insulation. Let's finish off question 7.52 with part C. We are asked to understand and calculate the varying temperature of the conductor, both bare and with insulation, with a range of wind velocities in the range of 2 to 20 meters per second. Now, this is clearly a question you shouldn't do by hand. You should do it by employing a software like Python or MATLAB, and that's what I did, and you can see the result here. So basically, you have I drew a line here, which I'm highlighting right now, which is the insulated conductor temperature, and the other one is the bare conductor temperature. Let's comment on this graph for 1 second. You can see that the effect of the 2 millimeter insulation layer is to increase the temperature of the cable by almost 22 degrees. I know you can't really see it from the graph, but it's about 22 degrees. It is important to say, though, and this is really crucial, that we did not account for a change in the electrical resistivity of the cable as a result of the increase in temperature. Yet, it must be noted that the dissipation loss, so Qgen, which is equal to I squared R, so the current squared times the electrical resistance, increases as the cable temperature, so the conductor temperature, rises. The last peculiarity I would like to show you about this graph is that, of course, the conductor temperature is inversely proportional to the wind velocity, because, of course, as the wind velocity increases, the conductor temperature decreases. However, what I also would like to show you is that at the beginning, so at lower wind velocities, the difference between the bare conductor and the insulated conductor temperatures is smaller than the scenario with higher wind velocities. Also, as we go on, the temperature difference almost becomes steady and doesn't change. Having said that, that is all for question 7.52. I hope it was clear, and please do not hesitate to contact me in case you do not understand any steps.